So let's see. Our first example. It is one of the easiest to calculate, and it's also one of the most common to use in an actual electrical circuit. And that is what's called a parallel plate capacitor. What's a parallel plate capacitor? Well, basically, remember we have two metal pieces, right, to form a capacitor. Both metal pieces, in this case, is a relatively large sized flat piece of conductor. Okay, so it's a large plane here, a large plane here. Now, when I say large, what do I really mean? Well, it doesn't have to be very large compared to, say, this desk. Okay, what I mean is that the size, the dimension of each of these metallic plates is a lot greater than the distance between these two plates. So anywhere you look at any point inside this region where it's in between these two plates, from your perspective, you were here, then when you look at this setup, you find that from your perspective, each plate appears to be very large. Now, why is that useful? Because that would mean that as a good approximation, everywhere that you look, you're pretty much far away from the edge. Okay, so you can think of each plate as virtually infinitely large, which can greatly simplify our calculation of its electric field. That is the only reason why we do that. Okay, so with that assumption, let us calculate its capacitance. How do we calculate capacitance again? Well, we put some charge Q here, and we put some charge negative Q here. Right? And let's see what kind of potential difference arises as a result. Now, of course, in order to do so, we have to hook up to a battery. Okay, that is how we actually do it in a real electrical circuit. So here's a battery. Look at the symbol of the battery. There's a long bar, there's a short bar. One side has a higher potential than the other side. So the battery really just like a pump. Okay, it pumps electrical charges from a lower voltage to a higher voltage. So guess which side has a lower voltage? The one with a shorter bar or the longer bar? Well, clearly it's the one with the shorter bar. Okay, that's how we symbolize it. So this longer bar corresponds to higher potential. This shorter bar corresponds to lower potential. The potential difference between the two terminals of the battery is V. Right? And then this wire is linked between this plate and the positive terminal. So this plate and the positive terminal will now share the same voltage. Okay? And similarly, the negative terminal of the battery is connected by a wire to the other metal plate, and therefore it will have the same voltage as the negative terminal. So if the positive and negative terminals differ by voltage difference V, then the same voltage difference will apply between these two plates. Okay, so we know clearly that the voltage difference between these two plates is now V. But as a result, they will have a Q and negative Q here. If we can calculate Q as something proportional to V, then we can take Q over V and we find its capacitance, right? So let's see how we can do that. Well, if we know the area A of each capacitor, of each plate, okay, this surface area A and the surface area A. By A, I mean this area facing each other, okay? It's the area of my hand facing each other. If we know the area A, then all I have to know is sigma, the surface charge density. Then I can find Q, right? So Q equals sigma A. Okay, Q equals sigma A. But what about sigma? How do you find sigma? Well, you know, once you know sigma, you can find the electric field, right? Once you know sigma, you can find the electric field. Now, what I want to tell you first, you probably know that, but let's just review that, is that the charge Q here and the charge negative here, they must have the same magnitude. Okay, if this is, say, 1 coulomb, this must be negative 1 coulomb. No more, no less. And also, I want to show you that all the excess charges must be, for this particular plate, must be on the right side. All the excess charges on that plate must be on the left side, so that the positive and negative charges are as close to each other as possible. Nothing on this side and nothing on that side. Now that seems to make sense, because after all, you have positive charge here and negative charge here. They attract each other, right? So they want to get as close to each other as possible. But how do we know that this Q and that negative Q must have the same exact magnitude? Well, that in fact is not that hard to show. All we have to do is draw a clever Gaussian surface. Okay, so let's draw a Gaussian surface like this. Right. It's like a Gaussian cylinder, right? What we see is its side, the side of the cylinder. You know the electric field goes like this, right? In between the two plates. So there is no flux through the side. Okay, there's no flux through the side. What about the top and the bottom surface of this Gaussian cylinder? Is there any electric flux? Well, what is the electric field inside this metal plate? That's inside the metal plate, and therefore it's what? Zero, because there is no E field, right? And similarly, there is no E field there, so the flux is also zero. So the flux through the entire Gaussian cylinder is zero, and therefore, what is the net charge enclosed by this Gaussian cylinder? Well, it must be zero, okay? So any charge here must cancel any charge there, and it is clear, therefore, that if this is a Q, it's got to be negative Q. If this surface charge density is sigma, that's got to be negative sigma. Alright, now given that, next thing is, let us calculate the electric field here, in between these two plates, as a function of sigma. Okay, there are a couple of things we can do. One is we realize that the electric field here is a sum of these two fields, one produced by a positive sheet, the other produced by a negative sheet. They point in the same direction. Okay, they both go from left to right, and they're both equal to the same value of sigma over 2 epsilon naught. Okay, you double it, you get sigma over epsilon naught. That is the electric field. But another thing we can do is we can just pick up a point here, right? Let's say, and we realize that this point is right outside an ideal conductor with a surface charge density sigma, and therefore it is clear that the electric field over there, just like anywhere else, must be sigma over epsilon naught. Okay, so anyhow, you find the electric field. Okay, this is the electric field pointing from left to right. It is uniform, as we saw. In fact, we saw that example before. And therefore, what is the voltage difference between here and there? V would be equal to the integral of E dot ds, right? Going from here to there. And E and ds have the same direction. So this is just E ds. And E has the same magnitude, E integral over ds. And what is the integral of ds from here to there? That will be just the distance between the two plates, right? The separation, d. So this is E times d, all right? That is clear, of course, because the electric field is uniform, okay? That's how you calculate the voltage difference for a uniform electric field. And E is sigma over epsilon naught, then times d. This gives us V. Okay, this gives us V, and what do we do next? Well, let's take Q over V, because that's what we want, right? We want to know C. That's defined as Q over V. All right. That's Q over V. Q itself is sigma times the surface area A of each plate. The reason why I want to do that is because there is a sigma here, so I want to cancel that out. Okay, you divide it by V, which is sigma d over epsilon naught. So you see sigma and sigma indeed cancels out. You're left with epsilon naught A over D. Okay, this is the electrical capacitance of a parallel plate capacitor. Now, if you take a look at this versus the example we had before, the capacitance of a single spherical conductor, the result we got over there was 4 pi epsilon naught times r. Forget about that 4 pi, okay? There is an epsilon naught here, and it's just like there is an epsilon naught there. What follows is a single radius, single dimension. So, in this case, the capacitance is equal to some numerical constant 4 pi times epsilon naught times some sort of length, okay? Some sort of length. Same thing here. It's epsilon naught times some sort of length, because the area over distance, as you know, dimensionally is length. Okay, keep that in mind, all right? The capacitance dimensionally is always that of epsilon naught times some sort of length. And again, since epsilon naught is an extremely small number, unless the dimension following that is extremely large, you are going to get a very small numerical value for the capacitance. And therefore, when farad is extraordinarily large, we usually end up with, in a common electrical circuit, we usually use something like microfarad, something like nanofarad, or even picofarad. As a matter of fact, even millifarad is relatively large. Okay, so this formula tells us that in order to increase the capacitance of a parallel plate capacitor, what we need to do is make the area greater. First of all, make the area greater, and secondly, put them closer together. Okay, let's see if that makes sense, right? Suppose you put the same amount of charge Q on these two plates, but you make the area of each plate much greater. What does that do to you? Well, it will reduce the surface charge density, right? For the same Q but greater area A. When sigma is smaller, the electric field is also smaller, and that will reduce the potential difference, and therefore increasing C, right? On the other hand, if you reduce D, keeping everything the same, you reduce D, you know V equals electric field times D, right? If you keep the electric field the same, but you keep the plates closer, make D smaller, you can also reduce the potential difference, and therefore you can also increase C. So it makes sense that C is proportional to the area of each plate and inversely proportional to the distance between these two plates. So that is our first example, the parallel plate capacitor. Okay, as we saw before, the value of the capacitance of a capacitor depends on the geometrical setup, such as the shape and size. And moving from a parallel plate capacitor, the next type of capacitor we're going to study has a different geometry. It's a cylindrical capacitor. Okay, so imagine I have an infinite long cylinder made of metal, made of conductors, and it's surrounded by a concentric shell of infinite large, which is also infinite long. Okay, cylindrical. Now the reason why I want to make them infinite long is because that way we can easily calculate the electric field in between the cylindrical conductor and the cylindrical shell. Otherwise, the electric field would depend on how far you are from the ends, and that will make things more complicated. Okay, so we basically have infinite long concentric cylindrical capacitor with an inner cylinder and an outer conducting shell. Okay, the radius of the inner cylinder is A, and radius of the outer shell is B. And in between A and B, there is an electric field, radially outwards, of course. What I'm going to do is I'm going to charge the inner cylinder and outer shell so that the inner cylinder is positively charged, the outer shell is negatively charged. There is now a potential difference between here and there. If we calculate that potential difference, then we can start from here and find the capacitance. Now, one thing you want to pay attention to: if you charge this cylinder uniformly to a certain charge, to a certain linear charge density lambda, or charge per unit length lambda, what is the total amount of charge that can be carried by this inner cylinder, which is infinitely long? Well, wouldn't that be infinity, right? So if you want to calculate the capacitance of the whole thing, it's going to be infinitely large. Okay, and that makes sense because, you know, the bigger the dimension of capacitor, the greater its capacitance. Now it's infinitely large, therefore you have an infinitely large capacitor. Okay, capacitance. But that obviously is not something we want. We want to calculate, therefore, capacitance per unit length. Okay, not for the whole thing, but only per unit length. So let us only look at the charge carried per unit length, which is just lambda. And we're going to take that lambda divided by what? By the potential difference between these two. That is the capacitance per unit length. Okay, that's what we're looking for. All right, let's see how much that is equal to. Well, to do so, we have to calculate V, which hopefully will be proportional to lambda, right? So that we can take the ratio and go what we want. So this really is not C, rather C over L, L being the length in this direction. Okay, so it is capacitance per unit length along the cylinder. All right, let's find V. V is the integral of electric field E between here and there. So let's first establish the electric field expression between here and there. And we've done that a number of times before in previous chapters. So E between A and B. Okay, if I use a radius R, this is radius R. We know what that is. That will be equal to lambda over 2 pi epsilon naught 1 over R, and here is the direction. I hope just to remember that. If not, make sure you know how to calculate that. Okay, review the previous couple of chapters. It's all there. We did that more than once. Okay, so it's not a constant, but you can easily integrate between here and there. So what is V then? We integrate between the inner and outer surface. Okay, so between A and B. dot dr, or E dot ds. ds and dr are the same thing, going this way. E and ds have the same direction, they're both really outwards, so this really is just a to b E dr. Okay, E is right here. E is lambda over 2 pi epsilon naught r. So I'm going to take that lambda over 2 pi epsilon naught. These are just constants. 1 over r dr between a and b. Okay, you finish this integral, you find it's a natural log function. Lambda over 2 pi epsilon naught, natural log of b over a. Okay, b over a. Given that, we can then find the capacitor per unit length, which is lambda over v. So therefore C over L would be simply equal to lambda divided by this, okay, by lambda over 2 pi epsilon naught natural log b over a, and the lambda cancels, that's what we wanted, so it is equal to 2 pi epsilon naught divided by natural log of b over a. Okay, now natural log has no units, no dimension, so this just is a constant, some numerical constant times epsilon naught. What happened to the length? Well, it's divided off here. See, it's charge, it's capacitance per unit length. You can move the L over, then you get the full capacitance for an entire length L. Now, you notice that this expression looks very different from the previous case of parallel plate capacitor, which had no natural log function, right? It was just epsilon naught A over D. However, there's an interesting observation, and that is, when you move this cylinder, make it greater and greater and greater, so that A is almost equal to B. Okay, so you have basically two concentric, there's a concentric cylinder and a shell, but they almost have the same radius. Okay, so look at something like this as a top view. Okay, look at something like this. Here is the shell, and here is the cylinder, and the gap between them, which is B minus A, is very close to 0. Alright, then imagine you look at a point inside this gap. Now, from the perspective of this point, both the shell and the inner cylinder look very flat, right? Look very flat, and therefore the radius of each of them is, relatively speaking, almost infinity. So, because of that, they will resemble what? An infinitely large plane, right? This suggests that if B is roughly equal to A, okay, or more precisely, if B minus A, the distance between A and B, divided by A, is much less than 1, all right? The gap is much less than A, then we will find that this geometry and the parallel plate capacitor geometry will become pretty much identical, because the region in between these two conductors will look very flat. Okay, the curvature here is almost 0, and you should get the same result. Is that so? Well, let's call the distance between B and A, we call it D. Okay, so D is defined as B minus A. Okay, B minus A. And then we can write this B as A plus D, of course. So V, which is equal to, I'm sorry, forget about V. Let's just use C over L. So C over L is 2 pi epsilon naught natural log. Instead of B over A, I'm rewriting B as D plus A. Okay, so it's A plus D divided by A. There is no approximation here, but if I rewrite this as 2 pi epsilon naught divided by natural log of 1 plus D over A. And you notice that D over A is very close to 0. It's much less than 1. Is there a way we can simplify this natural log function? Well, if you recall from your math class, natural log of 1 plus x, when x is very close to 0, it's far less than 1, how much is that roughly equal to? That is roughly equal to x. Okay, check your math book. And therefore, if I take x equals D over A here, so this will be roughly 2 pi epsilon naught D over A. Okay, instead of log of 1 plus x, let's just use x. And let me flip it A up. That is 2 pi A times epsilon naught over D. If you move that L over, things will even get better. You move that L over, okay? Move that L over. And therefore, C is roughly equal to 2 pi A L over D times epsilon naught, right? Okay, exactly what is 2 pi A times L? A is the inner radius, and therefore 2 pi is the circumference, right? Times L, the length along the cylinder. What is 2 pi times L? Isn't that the area of the inner cylinder? Divided by D, the separation. So then this becomes A over D times epsilon naught. That magically goes back to the same expression we have here, epsilon naught A over D. Okay, A being the area of each metal piece. Okay, of course, the outer cylinder has a slightly greater area, but it's almost the same as the inner cylinder because the separation between them is very, very small. So it goes back to the case of parallel plate capacitor under the right approximation. Okay, so we have studied a parallel plate capacitor which has planar symmetry, and then we have a cylindrical capacitor which exhibits, of course, cylindrical symmetry. So what's the only thing left to do? What's the third type of symmetry? Spherical symmetry. Okay, so we now have a spherical capacitor. It's made of, again, two metal pieces. I make them concentric so that the electric field is also spherically symmetrical, so that makes my job easier. So suppose I have a sphere. Okay, this time it's a metal sphere, radius A, surrounded by a spherical shell concentric with it of radius B. Okay, I charge this inner piece up with a charge Q, and the outer piece I charge with negative Q. Okay, I can do so by hooking this end and that end to a potential difference, to a battery, and then you're going to deposit a certain amount of charge here and the opposite amount of charge there. Let us calculate the resulting capacitance of this setup. Okay, now one can easily do that. Just like before, all we need to do is to find, suppose there is a Q here. Okay, suppose there is a Q here and a negative Q here. How does one find the electric field? Now, what's the electric field? How does one calculate V, the potential difference between these two? And then just take Q over V. Okay, so suppose there's a Q here. What is the electric field in between A and B? Well, if the radius is R, then if you pick up a point here, using a spherical Gaussian surface, you'll find the only charge you capture is this Q. There is nothing captured on that surface, and you get a spherical Gaussian surface, and the result would be the electric field of a point charge centered right here. So E is equal to 1 over 4 pi epsilon naught Q over R squared. Okay, it's a point charge, right? And then unit vector along the R direction. And then we're going to easily calculate the potential difference between here and there. V is just the integral of E dot dr, or ds, the same thing. Okay, radially outwards between A and B. Alright, let's easily finish this integral. Take all the constants out. Q over 4 pi epsilon naught 1 over R squared, and then R, the unit vector R dot dr, okay, between A and B. Now R dot dr, R and dr have the same direction, they're both sticking outwards, and therefore this is just dr, okay, just dr. So this is Q over 4 pi epsilon naught integration from A to B, 1 over R dr, right? Actually 1 over R squared, I'm sorry, 1 over R squared dr. And then the answer would be negative 1 over R, and you go from A to B. So if you finish the algebra, it's Q over 4 pi epsilon naught 1 over A minus 1 over B. Okay, now this is the same as Q B minus A divided by 4 pi A times B times epsilon naught. Alright? With that, we now can figure out C. So what's C equal to? C equals to Q over V, right? Q over V, and that's Q divided by this whole thing here, by Q, then B minus A divided by 4 pi epsilon naught AB. I'm going to flip that up, so it's 4 pi AB epsilon naught. Q and Q cancels. You're left with epsilon naught times 4 pi AB over B minus A. Okay, this is our answer. Now, if you check the dimension, hopefully we'll get the right answer. Epsilon naught times some sort of length. Is that length? Yes, it is. A times B divided by B minus A. So it's some sort of length, which is correct. And just like the case of cylindrical capacitor, does this answer revert to the case of parallel plate capacitor under the right approximation? Well, what kind of right approximation? You want to turn these curved surface into a flat surface, right? And that happens when the radius becomes very large. In other words, you want A to approach B. Okay, so this gap becomes extremely narrow. So from any point inside the gap, this sphere and that sphere look very much like infinitely flat, infinitely large, and therefore flat. So if I take B minus A to be very, very small, okay, so B minus A, which I call D, is far less than A. Alright, what does that become? Well, epsilon naught times what? 4 pi AB. Now remember, A and B are almost the same. Okay, it's either 4 pi A squared or 4 pi B squared. But wait a minute, what is 4 pi A squared anyway? 4 pi squared, isn't that the surface area of the of this inner sphere? Right? So it's just A divided by what? B minus A, and that's just D. You see that? Once again, it goes back to the case of parallel plate capacitor when the approximation is right.